All right, so we have that a milk processor monitors the number of bacteria per milliliter in raw milk received at the factory. A random sample of 10 1-milliliter specimens of milk supplied by one producer gives the following data. And we got to construct and interpret a 90% confidence interval for the population mean mu. Okay, so here again is another good example of a free response type problem that you may get on your AP exam. So I'm going to go through the 4-step process that will really help you ensure that you get all the key points that the grader wants you to mention. That way you get full credit on these types of problems on your AP exam. So first we're going to organize our thoughts into our state section. And here we're going to say that we want to estimate the true mean mu, which is the true mean number of bacteria per milliliter at the factory at the 90% confidence level. So let's write that we would like to estimate the true mean mu, which is the true mean number of bacteria per milliliter in raw milk. In raw milk at the factory with 90% confidence. So the two key things you want to address here are that what you want to estimate the population parameter and what it means and the level of confidence. So make sure you hit those two. Next, we're going to mention our plan. So our plan is to construct a one sample t interval for mu as long as the conditions are met. So we will use a one sample t interval if conditions are met. And the three conditions will be the random, 10%, and then the normal large sample. So the random condition, we know it's met because it says that they took a random sample. So we can say that's met. To 10%. We can say that this is met because there's going to be at least 100, 1 milliliter specimens of milk in the population. So, that's kind of, something you kind of just have to say we could assume is met. So we'll say n is 10, and we're basically population size is at least 100. So that's met, that's met. And then the normal large sample. Now, we're not told that the population distribution is normal, and we're only given 10, 10 specimens. So that means the normal large sample is not met because we have to have at least a sample size of 30. However, what we do in these cases is we want to inspect the shape of the sample data and be able to reasonably conclude that we can say that the distribution would be approximately normal based on the distribution of the sample data. So we're going to make a box plot of this data and draw a sketch of it and see what we got. So I have entered the data in my list, my calculator. I'm going to plot this. Go to plot. Make sure all your other graphs are off. And in this calculator, select the first box plot, because if you see the difference between these, we have two box plots. This first one's going to show outliers as distinct points with spaces between the rest of the box plot. So then this could let you visually see if there are any outliers. And I'm picking list 3. The mark doesn't matter. So let me go, let's graph see this. All right, and here's a box plot, and it doesn't look like there's any outliers and there's no extreme skewness. So we're going to draw a sketch of this. And based on this, it's reasonable to move on with our inference method. And again, just draw a sketch. I usually just highlight the five key points on the box plot when I draw my sketch. Don't waste too much time about drawing it super detailed. So let me draw a box plot here. My max 5370 and 5150 at Q3, median 4895, 4760, 4500. And I don't even think they really mind if you don't mention these 5 points. I like to just do it anyways. So, and we can say again, let's mention that box plot shows no strong skewness or outliers, so it's reasonable to move on. So now we do our do part where we run our calculation of our one sample t interval. So this is, remember, the sample mean plus or minus t star times the sample standard deviation over the square root of the sample size. So let's figure out what these would be. Since we have the values in our calculator, we can go ahead and just run the one variable statistics. It's in list 3 for me, so I'm going to enter list 3. And my mean is 4950. My sample standard deviation is 268.45. My sample size is 10. And my T star, since we're looking at 90% confidence interval, to find T star, remember, we got to use degrees of freedom, which is 1 less than the sample size, so the degrees of freedom would be 9. So I can then move on to my table B, which is going to be on your formula packet for the 90% confidence interval. Remember, down here is going to show the confidence interval. And I'm going to look in the row that corresponds to 9 degrees of freedom. So this one right here. And it'll be a 1.833. Be my T star. So from here, this just becomes an algebra problem. This just becomes 4950 plus or minus 1.833 times 268.45 over the square root of 10. Let's see what I get. 268.45 divided by the square root of 10. And you have a 155.6 from a margin of error. So then 4950 plus or minus 155 point, I'm gonna go 0.61. So add and subtract that from 4950 plus 4950, 4950 minus, and that will give me my upper and lower bounds. My confidence interval would be from 4794.4 to about 5105.6. All right. And the last thing is just to complete write our do part. So let me go into this. I ran out of space here, so or to interpret our do part in context. So that'll be our conclusion, or conclude, we would say. So we now just say that we're 90% confident that this interval captures the true mean number of bacteria in the milk received at this factory. That's the interval 4794.4, 51.05. In the milk received at this factory. All right, and there we go. I hope that helps.